Okay, so quantum physics is, totally, it's if you go for upper level undergraduate physics class, there is whole class offered for the quantum mechanics. So yes, it is fantastic. It covers a lot of material. But here I want to just introduce you to what quantum phenomenon means and what challenge the physics. Okay, let's say the physics we have learned so far, that physics is not enough to explain, that wasn't enough to explain some of the phenomenon experimentalists started observing towards the end of 19th century or 20th century. Okay, so any physics that is, like let's say taught, you know, all the physics we have learned so far, except the theory of relativity, that's counted as a classical physics. Okay, and then there needed this introduction of quantum of the thing, quantization of the thingy, and any physics that uses that concept of quantization, that's now called modern physics. Okay, so that's the cutoff between them. And what is quantization means? So there is one phenomenon in classical physics that demonstrates the quantum physics very well. Okay, so here is this video, and yes, I got this from YouTube, but looks like I forgot to include the link here. I should, yeah, I'm kind of sorry about that. But let's watch this video here.
To what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on. Well, let's go higher. So it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. But if I set it here, for example, I have what's called a standing wave. That is, the wave that's sent down and reflects constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice this is a node, and the middle is a node. So we have three nodes for this wave. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump ball. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess, what is that, around 25.5? And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1.5. 1.5 wavelengths. And it's easier to see in high speed. So check out this shot with the high-speed camera and verify for yourself that it is 1.5 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
So we're going to come back and talk about this one a little bit, okay? There are some screenshot of that kind of experiment. So why am I showing this one here? I'm going to try to explain that, okay? So for now, what you want to keep in mind is that for first harmonic, or let's say when it was just oscillating up and down with just making one envelope, nodes on the side, just one antinode in between, right? So that occurred around 8.5 hertz. And then one with the 2 envelope occurs exactly at double of that. So whatever that fundamental, that's also called fundamental frequency, okay? So now the next mode occurs exactly twice. And then the other one occurs exactly at the third, 3 times that frequency, 3 times the fundamental, and so on. So you can see there is 1 times fundamental, 2 times fundamental, 3 times fundamental. So integer multiple of the fundamental. So when we have that kind of situation where there is this integer multiple times kind of situation occurs, we say that's the quantization. That's all it, quantization means just that. It's a discrete, okay? So later in another chapter, we'll talk about how the electrons that's orbiting around proton in an atom, right? They can jump from one state to another state, but they cannot just go anywhere in between. So there are well-defined states, and we call that quantum states. So basically, explanation of that can be also, embedded, or we can use the video we just saw to explain that why there is no intermediate steps. There are just discrete steps. So just like we saw, it was the standing wave that was forming, and the standing wave, so frequency is related to energy. We'll soon see that, okay? So what happens is when we look at that envelope, it has a certain frequency, and then the next envelope occurs at double of that frequency. So when electrons goes around, it kind of generates a standing wave, just like the wave in a string generates a standing wave, okay? And then what happens? it can vibrate with certain modes. So each mode gives you each orbit for the electron. So at higher level, you have now one with the double envelope. One with just one envelope, that's a ground state, and so on, okay? So that's the quantization. That's the quantum physics, and if you learn that in chemistry, probably you learn that as a quantum chemistry, okay? So that's what the quantum is. So here is an example to understand that quantum nature. So for example, when you go on a wheelchair, let's say, or you drive a car in a ramp, you can be at any height. You can be at any height. So each height gonna give you a particular value of potential energy, right? Now, if you take a stairs or steps, what happens? You have now just a well-defined height. This is, let's say if this is h1, this is 2 times h1, okay? And this is 3 times h1. You cannot stand at 2.5 times h1, okay? So there is no continuous value. What happens? There are only discrete values available. That's what the quantization means, okay? So in our video, that's what we saw. What happens? In one frequency, in that video, that frequency was 8.5 hertz. And this value depends on, like how tight the string is. Mostly it depends on that, okay? So you can change that value. The value of fundamental you can change, but then what happens is the second gonna be exactly 2 times and 3 times and 4 times and so on. So it becomes n times. So it's quantized, okay? So there are only certain things we can visualize about, like a quantization of thingy. And mostly this quantum phenomenon occurs in atomic scales. Okay, we don't see or we cannot observe the quantum phenomenon for the motion of object like a larger object. For example, when we are walking, we don't observe that, okay? But when electron is orbiting around, it exhibits quantum phenomenon. So we can say, okay, these frequency in this standing wave, they are quantized. And since frequency is related to energy, what happens? We find energy quantized in the atoms, okay? So that's just like we saw a frame of that video, right? So now, just like I said, why we needed to insert quantum mechanics? Because there were some experimental observation that we could not explain by using the physics up to that time, what we call now classical mechanics, okay, or classical physics. So one such famous experiment that kind of broke down or we could not explain by using classical physics was this blackbody radiation. So what happens? When we heat a filament, it emits light and heat, and that's what the light bulb is, or at least the traditional kind of light bulb that has a filament, right? When you heat iron, what happens? It glows. First it glows red, okay, red hot, and then what happens? And then it becomes yellow hot, and then it becomes blue hot. And then finally, as you keep on increasing temperature, what happens is it becomes white hot. So what does it mean is it is emitting that light. For example, at certain temperature, it emits red light. When temperature increases, same iron emits the yellow light. And then at higher temperature, what happens? It starts emitting blue light. And when it starts emitting all lights, then we see it as a white light. So that's what you see here. If you hit something, what happens? It glows, and then it emits these different radiation, okay? And red first, and if you go higher, then what happens? It becomes a yellowish, and then becomes a bluish. And when it's emitting everything, all color, it becomes white. Okay, so that's what you see here. So it is at higher frequency, okay? And this light bulb is emitting all light, all color mixed up. So that's why we see kind of white light there, okay? So now, what happens is that there is this classical theory that describes how much energy comes out when we increase the temperature of certain object, okay? So that's called Stephen's-Boltzmann equation here, or Boltzmann law, Stephen's law, I should say. Yeah, I think both gentlemen, contributed to that law, but yeah, Stephen's law here. So what it is saying is the energy that comes out is proportional to the fourth of the temperature in Kelvin, okay? So energy coming out, and when we measure the energy that's falling on the surface per unit area, we call that intensity, and that's what we are plotting here, okay? So energy that we receive, the energy we are measuring, and that's what we are doing this, okay? And then what happens is that at first, at low temperature, for example, we are also emitting radiation. We have temperature, right? Our body temperature is around 98 degree Fahrenheit. I think if we convert that, it becomes slightly higher than 300 Kelvin, right? So if you were to plug that in there, that's the energy that's coming out from our body. So if we were to find wavelength of that, or the frequency of that, what happens is it is not in the region of the visible light, not in the visible light region. And any lower frequency, for example, radio wave, remember we talked about the spectrum. So radio wave and the infrared wave, heat wave, that we cannot see them. So our body is emitting warm heat, right? So because we have around this much temperature, and the related, the frequency, if we were to translate or get the frequency or wavelength based on this much energy, and then it turns out to be at the range of infrared, okay? So what happens is, when, as long as we, the energy is coming out at lower temperature or longer wavelength region, what happens? This law works just fine. But as the frequency becomes higher, rather than just keep increasing, see, it doesn't say it's going to decrease, because see, temperature is, increasing, means it simply predicts it's just going to keep rising as you keep on increasing temperature. But when people did the experiment and, did this plotting here for at different temperature for different frequencies, what happened was they found that, okay, it's not following the classical theory predicted by this law. So this law predicts this, but what happens? This starts carving down. So knowledge that we had up to that point was not enough to describe what we were observing by doing the experiment, okay? So that's when Later what happened is Planck's used this idea that energy is quantized and it is some constant times the frequency of the wave. So if I have, let's say, red light, okay, it says red light has a frequency around here. Looks like looking at this plot here, we can see it says it is around 4.4, 10 times negative, oh, not negative, but positive 14 hertz, right? So that's the frequency, that's what the F is here. And H is called Planck's constant, and it's very tiny, tiny, tiny number, okay? So when Planck used that idea and then modified this law here, the energy that comes out, okay, what happened is by doing that, he was able to come up with the equation when plotted like this. What does that equation gives? Exactly gives these values, okay? This curve, it gives that curve. So what does it mean? So without quantizing the energy, so at that time, the idea was that energy is just a wave, right? And it is a continuous thingy. They are not quantized. That was the idea. But when Yi used that idea of quantization, what happened? He was able to describe this experimental observation. So what does it mean? That means indeed energy is quantized. And how much energy, so how much, like let's say, what's the smallest amount of energy a quantum of energy gonna have? And that is given by this equation. So if that energy is coming from a wave that has a frequency f, you just multiply that by this constant, and that's gonna be that. So if we have, let's say, higher energy, what that means, more intense energy, that means it's a 2 times or 3 times or 1,000 times, okay? So that's how the energy comes out. So that's how he described it rather than using this, okay? So this is Planck's constant. As you can see, this number is really, really small, okay? So for any oscillating particle later, like this equation of oscillation uh, was derived, in terms of the frequency of oscillation. And this quantization of idea, sometimes I like to describe by saying like, it's like a ATM machine. What happens? If you go to the ATM machine and if you try to get $7, you cannot get it. If you try to get $12, you cannot get it. If you try to get $22, you cannot get it. It has to be multiple of certain bill, for example, 10, 20, or 20, 40, something like that, okay? So that's the quantization. So it's just the discrete values, that's all it means, okay? So any oscillating particle has this energy, and that is some integer multiple of h times f. So that's how it was used to derive this equation, this relationship that gave this kind of plot or verified this experiment, okay? So here what you want to take out is that quantum of energy is given by hf. Any higher amount of energy from that particular frequency going to be 2 times that, 3 times that, and so on. So they are quantized, right? So that basically came, like this idea was first used by Planck, and same idea was used to, describe this experimental phenomenon. And this sun here looks like a kind of red or yellowish because it has the temperature, the surface temperature. As you can see here, what happens is the surface temperature, I think, is around 4,500 Kelvin, 5,500 Kelvin, in that range. So what happens is in that range, object emit mostly yellow light. Okay, so that's why the sun appears to be kind of yellowish. Okay, and probably you may have noticed these light bulbs, they are rated at different temperature. So for example, there may be a light bulb that's rated like 3,700 Kelvin, and a light bulb that's rated to 5,000 or even 6,000 Kelvin. So what happens? They are, you know, like giving up kind of bluish light, and this one is giving more like a yellowish light. Okay, so warm light and then, you know, relaxing mood, that's what you want. You use little bit lower temperature light bulb, right? So it emits kind of yellowish kind of light. But if you want to be awake, that means it's like a daylight. That's what our body used to, right? So during daytime we are awake. So daylight time of temperature is, you know, mimicked by using a light bulb around this temperature. Okay, so basically that's what this curve is. Okay, so here is only up to 3,000 Kelvin, right? So if you go higher than that, then what happens? This starts picking up near red, more towards red, and then more towards yellow, and then that. So the peak keeps on shifting as temperature increases. And what that means is more intense light coming out is of that particular color. Here, it's not producing any intense light here at this temperature. You have to go a little higher than that, okay? Okay, so now here is a question for you. So try to answer based on what you just learned and what you know about the frequency of different waves from electromagnetic wave chapter, right? And you have a minute to answer this question. Oh, 20 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So just like we saw here, what happens? The frequency kind of is going from red to yellow to the green to the blue to the purple and then ultraviolet, X-ray, and so on. Okay, so that's what happens. So among the given ones, looks like the green has the lowest one. And that's what most of you looks like chose, right? So frequency and wavelength, they are inversely related. Okay. So X-rays, among these, X-ray has shortest wavelength. X-ray has shortest wavelength, but largest frequency. Okay, so this has the shortest among these. It has the largest. So they are inversely related. So probably if you're, if you chose A, probably you were thinking in terms of, let's say, wavelength. But remember, the energy is H times F. But yes, we can write this in terms of wavelength as well, because frequency, remember, the speed is frequency times wavelength. So we can write that. So they are inversely related. Okay. So now let's make use of that here. Red light coming out from a laser pointer has a wavelength of that much nanometer. Okay, so it says wavelength is 634 nanometer. So that's the wavelength of red light. Okay. So we need to convert this into meters. Nano means 10 to the power negative 9. Remember, milli means that many meters. Micro means that, and then thousandth of that gonna be the nano. Okay, and after that it goes pico, and then femto, and so on. So anyway, let's leave it there. So that's why that's what we use for the nanometer. And how many photons are coming out every second? So number of photons times the time interval. So remember, so what happened? One quantum is just h times f. So more energy means larger number of photons times hf. So whatever it is. So let's say where n is the number of photons. Okay, so it says photons per second every second. So that means we need to divide that by time. And what do we know? We are given power. Okay, so power, I'm using uppercase P here, is 5 milliwatt. So let's convert that into watt. Milli means 10 to the power negative 3, means it's going to be 5 times 10 to the power negative 3 watt. So now, power is the rate of change of energy. So what do we know? Power is rate of change of energy. So what rate energy is coming out? So an energy is related to work. In physics 1, probably you remember from physics 1, we said, okay, if somebody is doing same amount of work but faster, that means that person is using more power, right? So that's the rate of change of energy. Yes, in this class, we used power as I times V, current times voltage, or B square over R. So what this means in this case, how much electric energy is being converted into other form of energy. So that's how we are using here, okay? This or I square R. So for example, if we are using a current to produce light by attaching a light bulb in a circuit, what happens? The light bulb is acting like a machine that's converting electric energy into light and heat energy. in our conventional light bulb, most of the energy comes out as a heat. So that's why the light bulb becomes really hot right after, after just few seconds after you turn this thing on, okay? So most of it comes out as a heat. And that energy is I square R. So if we divide that by, oh, that's going to be the power actually, because the current has a time in it, charge over time. So that's the rate of transfer of energy or conversion of energy, electric energy. So we wrote that for this class here in physics 1. That's where we define power first, and we use this equation, right? So now, in this case, how do we write energy? There is no current, there is no force. So for example, if we had a current and voltage, we would write power as I times V. We don't have that. If we had force, displacement, and so on, that would be work done, and that work done gonna be equivalent to change in energy. We don't have that scenario here. Rather, what we have is the wavelength, and we know wavelength and frequency are related. And Planck's law told us that energy can also be written as, this can be written as h times f over time interval. So Planck's constant, it does not change. A frequency does not change. So nothing is changing here. So we don't need to worry about writing delta here. So we can simply write that as a h f over delta t. Okay. So now we have f in the equation, but what we know is wavelength. So that's why we need to write this frequency in terms of wavelength. So when we do that, what happens? Frequency is c over lambda. So that's what the frequency is. Okay. And we already have delta t. And by the way, one thing here that I missed is that this HF is just the energy from one photon, right? But it did not say it was just one photon. It's saying how many photons are coming. So for the total energy, what we need is we need to multiply this HF by N. So that's what I was talking about. So maybe I should insert that one right there, okay? And N times H times F, so N, right? So that means we are looking for, oh, that looks like a H, N. So we are looking for this, okay? So we know power, and we are looking for this. So that means let's solve for this. So N, maybe I should rearrange this equation. So N, H, N, H, C over delta T times lambda. I'm just copying that and I'm just switching the sides, okay, so that I can solve for N over delta T. Gonna be what then? So it's gonna be power times wavelength divide H times C. So these gonna go down here, right? And this wavelength gonna go up there, cross multiplication, or when we switch the side, what happens? Multiplication becomes division and vice versa, right? So we know that. So that's the number of photon coming out per second per unit time. Okay, so that's what that is, and that's what we are looking for. So now we can plug in all the things that we know. So all are in SI unit, so I'm just writing numbers here. Yeah, so this modern physics, it has, large or smaller number, so we need to deal with a lot of exponents. So H, Planck's constant, how much was that? 6.6 times 10 to the power negative 34. And c is the speed of light, which is 3 times 10 to the power 8. Okay, so this number being very small and it's dividing this thingy, what happens? We get large number here as the answer. Okay, do I have answer for this? No. So I think you get this really large number. Yes, of course I don't remember, but 9 and 3 becomes negative 12 here. So positive 8 and 34 is 26. So yeah, in the order of 12 to 16, something like that, okay? So even a tiny laser light is emitting that many photons, trillions of photons every second. That's how much it's coming out. And remember, that's just 5 milliwatt. And the light bulbs we use these days are, even if you are using, let's say, LED light bulbs, they may be 11, 12 watts, okay? So that means a lot of photons are coming out. So that's what it means, okay? So now we're going to be talking about another experiment to explain that phenomenon. We needed this quantum nature of energy, okay? Without that, it wasn't possible to explain that. So this is photoelectric effect. So light hits the metallic surface, and then what happens here? It can eject electrons. Okay. So now we have this technology. Remember all these photocells, this solar panel, they are using this principle. Okay, so what happens? The sunlight hits the solar panel, right? And then ejects electron, and we capture those electrons and let them flow or make them flow in a wire. And we can charge a battery, or we can directly put that in a circuit and use it, okay? So we are using this principle here. And to explain that principle, what's going on here, we need this concept of quantized energy. So what's happening here? Remember, according to classical theory, the light is going like a wave, right? So that's what we learn about, interference, diffraction, right? So wave is making this particle come out. How is it happening? Okay. So based on classical theory, what we can say is, okay, so this light has energy. So this one, the electron captures that energy. And then when it has enough energy to break that bond from the surface, right? So this is metal. So metal has electrons that can move from one lattice to another lattice on the crystal, atomic crystal, right? So what is one lattice? So there is one, let's say, nucleus, and electrons are orbiting around. But the outermost electron in metal, what happens is they can hop, or they can just go from one atom site to another atom site. So this is like they can visit neighbors, okay? So this electron, they can visit neighbors, but they cannot just jump off from that crystal. So when they capture energy, what happens? They can just break that bonding between proton. Remember, the electrons are orbiting around because there is force of attraction between proton and the electron. Now, If the electron has large energy suddenly, then what happens? It can just get out. Now, based on classical theory, what do we know? Okay, we can keep on supplying energy. So for example, we can keep on the stove. We can keep the stove on until water boils, and then water molecule starts becoming what? Vapor, and leaves the water surface, right? So it's like these water molecules are boiling off and becoming vapor. So something like this is happening here. So electron looks like, it's boiling off. So just like we can keep on heating, supplying energy until it has enough energy to leave the surface, right? Similarly, we should expect, so based on classical theory, we expect, okay, if we keep on shining on that light long enough, then this electron should come out based on classical theory. But what happens is that no matter how long you keep shining up with the light that has a lower frequency than a certain value, then this electron never comes out. So that's the interesting thing here, okay? So that's the main difference here. So based on classical theory, what happens? Let's say if we are shining with yellow light, and we know yellow has the, lowest frequency, means lowest energy, right? What happens? If we are shining with the yellow light, if we were to keep shining with the yellow light for long enough, then the electron should keep absorbing the energy. And once it has enough energy, it should come out, right? That's what we expect based on wave theory, classical wave theory of light. But what happens here is, no matter how long you shine this with the yellow light, it's not going to come out. But if you shine with the blue light, what happens? It instantly comes out. It doesn't even wait. So how do you describe that? That was the challenge, okay, for the classical theory. So what happens here? Electron has that much charge, and we know work done on moving some charge is given by Q times delta V, right? So we learned that, and so that's the energy of that charge. So in this case here, that is the electron, charge of an electron, and let's suppose if we can stop this electron from flying by using that much voltage, that means we can tell, okay, this one has that much energy, right? So this is called stopping potential, and that must be equal to the kinetic energy of that electron, speed with which it's coming out, right? So by doing this experiment, we can actually find, we can, find the speed with which it comes out or how much energy it has, okay? We can do that. So so what do we see in the experiment? If we have a brighter light, then more number of electrons comes out. And how much energy is there? When we measure that, kinetic energy of that, it's not giving higher kinetic energy, okay? If you are shining with certain color of light, it's giving you just one value of kinetic energy. Shining up with the brighter light based on the wave theory, what does it mean? Brighter means it has, more intense means it has a larger amplitude, right? We learned that intensity is directly proportional to the square of the amplitude, right? So more larger amplitude of wave means it's more energetic, right? So we expect brighter and brighter light should give you higher and higher speed, or it should give the electron higher and higher speed. That's what we expect. But what do we get? Nope, we don't get higher speed. Okay. But that speed depends on the frequency. Just like I said, if you go higher and higher frequency, what happens? Even if the light is very, very faint, what happens? You get the electrons coming out really fast. Okay. So it depends on the frequency. And if you go frequency lower than a certain value, it doesn't even come out. Just like I said, for example, yellow light may not eject any electrons, but the blue light can easily eject it, okay? Or red light may not eject it, but yellow light may eject it. So which light, which wavelength ejects, it depends on the nature of the metallic surface, okay? So classical theory doesn't set up that threshold of the frequency, okay? So based on the wave theory, what happens? You shine the brighter light, that means it has a larger energy. So just like the tsunami can, topple the buildings, collapse the building, right? Same idea. If you are shining with very bright light, that means you are bringing tsunami of light, and you expect a lot of electrons coming out with very high speed, okay? But instead what you get is, yes, you get a lot of electrons coming out, but not with higher speed. So that was the dilemma, okay? So what's happening, okay? Finding, explaining that was difficult, okay? And again, so based on the classical theory, what do we expect? If we shine for a longer time, like if we keep on supplying energy, eventually that should gather energy and come out, okay, should become more energetic. Just like I said, the water molecules, they can leave the surface if when we keep on heating them for a long time. But this electron here is not acting like that. But if it has frequency higher than the threshold, what happens is it just comes out. And it does not depend on the intensity. So intensity simply gives you larger number of the electrons, not faster electrons. So to explain that, Einstein came up with this explanation, okay? And that is now known as Einstein's photoelectric theory or equation. And Einstein is famous for relativity, but he won his Nobel Prize by coming up with this equation. At that time, it was a very difficult equation, okay? So this was experimentally verified. Actually, he actually explained the experiment. So there was proof. But for the theory of relativity, coming up with the proof, it took a long time. So it wasn't experimentally proved, for a long time. So that's why what happened? He did not get his Nobel Prize in the theory of relativity, rather he got this. So how did he explain? Okay, so he used this idea that energy is not coming from the amplitude E square, just like we say, we may think, okay, for the waves. So rather here, light is acting like a particle that has an energy H times F. So now it's like a particle of energy HF, and that particle is called photon, right? So what's happening is, it's like that particle, one particle is colliding with one electron. That's what's happening. If that particle is energetic enough, then what happens? this electron gets pushed out from the metal surface. But if this one photon doesn't have enough energy, then what happens? This electron cannot be pushed out. And this electron doesn't capture energy from another one, and accumulate that energy. What it does is it can just take energy from once, just like a collision between two particles, right? So for example, if you have a small rock here and there is another rock, and if you hit this rock with this rock, what happens? That intersection, that collision is one-time collision. So if this has enough energy, this is gonna just fly off from there. If it does not have enough energy, then what's gonna happen? It's gonna just stay there, okay? This rock gonna just scatter. It's gonna lose some energy. This rock that's coming out is gonna lose some energy, and it's gonna just scatter. And we indeed actually see that kind of phenomenon, and that's the Compton scattering later in this chapter, okay? So he used this idea of the particle, the light being not wave, but the particle with the energy this much, right? And those are the photons. So he used that idea and said, okay, it needs certain minimum amount of energy. That energy is equal to the energy required to pull that electron out from the bonding with the atom. Okay, so if that energy is enough, then it can pull it out. And if that energy is more than that, then what happens? This electron gonna get out from there and gonna fly off. An even higher energy photon gonna give it higher speed. So that's why there is higher kinetic energy. So that's what this equation is telling us. So there is this binding energy. Sometimes that is also known as work function for that metallic surface, okay? Work function. So minimum energy required is this. And if that frequency happens to be F0, then that's going to be equal to H times F0. And what happens? If the energy now, this HF, that means that's the energy of the photon, right? So that's the energy of photon. So it's when HF is equal to binding energy, which is HF0, certain value of that. If they are equal, then what's going to happen? Kinetic energy going to be 0, right? So difference is, did I write that? Let's say if HF is equal to binding energy, then this means this is going to be HF0. So HF0, so difference is going to be 0. So no kinetic energy. So what's going to happen? That electron going to just get out from there, but not going to fly off from the surface, okay? Now, if we sign with the higher frequency, then what's going to happen? Part of that energy going to go pull it out, overcome that binding energy, and the rest going to supply the kinetic energy. So the maximum kinetic energy we get just depends on the frequency we are applying, okay? So this pi, or binding energy, is constant value, and that depends on just the property of the metal surface, okay? So that's how Einstein explained why the kinetic energy was not increasing when you sign that with the brighter energy. Why kinetic energy did not increase? Because brighter light does not mean it has a higher frequency. So same frequency means it's not going to give you higher speed, but same speed. Kinetic energy means half mv squared, remember. So that's the maximum speed it can come out just depends on the frequency that's hitting the surface. So that's what it is saying, okay? So this is called work function. Hey, we passed our break time. So let's take break and we'll look at one example of using this equation to solve problem, okay? For reminding it, okay? So pi 0 here, that many electron volt, we need to convert that into joule. So that becomes that, okay? So 1 electron volt is that many joule. And the number is same as charge of an electron because it's charge of an electron times 1 volt potential difference. So when you multiply by 1, nothing changed. So only thing is that, okay? So electron volt check, you know, like let's say cancels, giving you that. So now whatever energy you get gonna be in terms of joule. So yes, so there are gonna be whole lot of number with a lot of exponents here. So that's H, and C is 3 times 10 to the power 8. And wavelength, that's a given wavelength we can use in meters, right? 386 10 to the power negative 9 meters. And minus pi 0, which is this number here. That means 2.34 times 1.6 10 to the power negative. So this is energy and this is also energy. So difference between energy we are talking about here, and that's going to be the joule. That's going to be the kinetic energy of the electron. But if you are asked to find speed, now what you can do, since Ke is, so this problem is done, but to find V, you can use half mv square as Ke, right? So for the Ke max, the speed. So the electron that comes out, the maximum speed the electron can come out depends on this frequency and the work function. And we calculated that. Now we can use that number here and solve for speed. And mass of electron, you can find that, right? It is in the order of 10 to the power negative 31. So it's a tiny, tiny thingy, okay? So that's how this thing works out. So now go ahead, take a look at this problem, and you have 1 minute and 30 seconds to answer this question. Twenty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So mostly the So what does the question say here? Kinetic energy. So energy, kinetic energy, Kf, Ke max is Hf minus pi 0, right? Work function, binding energy. So for a given metal surface, for a surface, this thing is constant. It's a constant for a surface. So now, when frequency changes, kinetic energy changes. But going from the yellow light to the blue light, is frequency increasing or decreasing or remaining same, right? So different colors, they have different frequency. And the blue, purple blue, it has the highest frequency. So that means that's going to have the largest kinetic energy. So it looks like yes. So maximum kinetic, blue going to be larger than the red. Yeah, red has the smallest wavelength among the visible light. So yes, that's D is the correct answer. Now let's talk about X-ray production experiment. So X-ray has one of the highest frequency. That means highest energy. It is very energetic, okay? So that's why when you go for X-ray, some sort of, let's say if you break a bone, what happens? They take X-ray, and when they take X-ray, what happens is they try to cover you other parts so that that part doesn't get exposed to the X-ray, because X-ray is a bit more energetic and it may interact with the let's say cell tissue in your body, and that may cause some sort of anomaly. Okay, that may happen. So because of that, what they do is they cover your body. So but how does that X-ray produced? So again, the production of X-rays can be explained by using quantum nature of the energy, okay? Just for the X-rays, yeah, we can just use the classical theory, but there is certain phenomenon that we observe while observing the X-ray production, and that cannot be explained by using classical physics. For that, we need to use quantum physics. And to fully explain that, actually, we need to wait until another chapter. Okay, but anyway, so let's talk about, how we generate X-rays. So for the X-rays, what we do is we use a filament here, metallic filament, right? And then you heat that filament, you make red hot. So by giving energy, just like when you supply energy to the water, what happens? Water kind of tries to boil off. Water boils off. So similarly, this electron kind of tries to boil off from that wire, okay? And then what happens? You apply very large or very high voltage. So here you can see the electrons, they have negative charge and they can come out from, so there are these electrons there in that wire, and you heat. So that means they start kind of vibrating and becomes kind of bit loose, okay? And when you supply with this high voltage, and see this negative is connected over there. So this negative gonna push this electron away, okay? So what happens is that negative voltage gives the kinetic energy to this electron. So this electron, when you use very high voltage, what happens? They're gonna come out with very high speed. So there is nothing quantum about it, okay? So in this case, EV is half mv squared. So that's what's happening, okay? So by applying voltage, that much voltage in one electron, you are supplying that much energy, and that energy is being converted into kinetic energy. Now, these electrons flying up really fast. And then what happens? There is this tungsten target, so metallic target like this. So electron is coming out, and then it comes to that target. So it hits the target, okay? So when it does, what happens? When collides, it loses energy, just like it comes here and hits on that surface. What happens? It slows down, right? So same idea here. The electrons moving really fast, collides to that surface. What happens? Loses energy. And when I do this, what happens? Sound energy comes out. But these electrons moving really fast. When they slow down, what happens is not just the, sound or heat coming out, rather, there are other waves coming out. That's the X-rays, okay? And very energetic waves that's coming out. Why? Because we are stopping very fast moving electrons, okay? So if the electrons are moving slower, then the wave that comes out are gonna be not so energetic as well. So by increasing voltage, what you can do is you can increase the frequency of the wave that's coming out. Remember, for these, so these are the X-ray photons that's coming out, we can say, okay? So that means they have energy, this, right? Each photon of the X-ray, they have energy H times F. And since the energy lost by this electron in that collision is really large because they were fast moving to begin with, what happens? The energy that comes out also has a very high energy, and that's why they go in the X-ray range, so they can easily penetrate through, let's say, our muscle, our cloth, our muscle, but they cannot penetrate the bones. So that's how we get the image of the bone, okay? Ordinary light, what happens? It cannot even penetrate through the muscle. So that's why we get the image of this outer body part, right? But for the X-ray, muscle is transparent. It can just penetrate through that, okay? But cannot penetrate the bone. So that's how it gets stopped, gets reflected, and that's how we get the image. Just like our body can reflect light and produce image, the regular image, similarly, we get X-ray image, okay? So that's how it works. But anyway, so that's how the X-ray comes out here. And we can write that equation something like this. So the maximum energy or the maximum energy of the X-ray photon that comes out depends on the kinetic energy, and that kinetic energy depends on the potential difference here, okay? So the kinetic energy depends on the potential difference here. So you can directly write that one as something like this here. So that's how this equation is related. So that means frequency depends on the potential difference. Okay. So now That means if you keep on increasing the potential, what happens? You expect to get higher and higher frequency X-ray, right? Okay, so far so good. We are not using any fancy physics here so far. But based on that equation, what do we expect is that, so certain frequency, it starts coming out at certain frequency because the B, it depends on B, right? And depending on how much B you are increasing, what happens? You may get a range of frequencies, certain range of frequency of those photons, the X-rays coming out. And most of them may be coming out at a certain frequency, and some of them may be coming out bit, lower frequency, because these electrons, when we are, applying the voltage, some electron may be moving a little bit slower than the other. Remember, they are just coming out in as a bunch over there. There is large traffic there, traffic of electrons, right? So in that case, what happens? Just like in the road, what may happen is there may be some vehicle moving a little slower and some may be moving a little faster, but most of them are moving with certain speed. So for example, if we have a freeway with a speed limit of 70, most of them may be moving with 70, but some may be moving a bit slower, some may be moving a bit faster, right? Okay, so that's what higher and lower frequency means. So this number of the electrons coming out, number of the photons coming out, what photon? Electrons come, the X-ray photons coming out is this. So that gives you the intensity, right? So you are plotting intensity here. So that gives you the number of photon emitted. So we expect that. But what we are seeing here is for certain frequency, there is certain burst of electrons coming out that we cannot explain by using the equation we wrote so far. We cannot. So what's happening here? What does it mean? So these peaks are called characteristic peaks. And to understand that, we need to go inside the atom and understand how these electrons are inside the atom, right? And why they are coming out. A lot of electrons are coming out at a particular frequency. So to understand that, we need to understand the discrete nature of these energy levels inside an atom. So in this case, we are using tungsten. So inside the tungsten, there are a lot of electrons. One in valence shell is getting, let's see, if we are just talking about electrons on the valence shell, that means that is the one that's coming out from the wire, and then what's happening? Getting accelerated by the voltage. But the electrons that's inside the valence shell are coming out at certain frequencies here. A bunch of them at certain frequencies. So why? Frequency is related to energy level. So this electron gets ejected from inside. So now, before, without knowing how electrons are at discrete level on the, when they are going around the nucleus, without knowing that, we cannot explain that, okay? And of course, in this class, we haven't talked about discrete nature of these electron energies inside an atom. So that's going to be the next class. That's the Bohr's theory we're going to be talking about, and you may be familiar with that, okay? So we need to use that discrete nature to explain this. So that's why this experiment is also important on going from classical theory to the quantum theory. So now here is question related to X-ray production, and you have a minute to answer this question. Oh, I forgot to warn. 30 more seconds, folks. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Faster X-rays. X-ray is electromagnetic wave. X-rays, they are electromagnetic wave. And all electromagnetic waves, they have same speed. C, speed of light. Light is also electromagnetic wave. So there is no faster or slower X-ray. All of them are moving with this speed once they are out there from the tungsten, okay? So this cannot be correct answer. X-ray is being produced having higher energy. So in this case, intensity means more photon, right? When the intensity of electron beam is increased, that means in this case, this is the electron beam. So that means more intense means more electron. Higher number of electron. That does not mean it has a higher energy. So energy, how much energy it comes out depends on how fast these electrons are moving, not how many electrons are moving, okay? So that's why both of these that is related to energy and wavelength are not correct. So more electrons means each electron, when slows down, what happens? Produces one photon of X-ray. Each electron produces one photon, right? So that means more photons are being produced when there are more electrons are coming. So yes, looks like D is the correct answer in this case. Okay. And how did you guys do? Hey, you guys did better than I do. Okay. So let's use that equation. So in this case, what's happening is that there are 88 kilovolt. So that means the potential difference here is 88 kilovolt means 1000 volt. Okay, we want that in volts to isolate electron from the rest. What is the minimum wavelength of the X-ray produced? Lambda minimum is what? So what happens? Lambda minimum means frequency maximum. Frequency maximum comes from the maximum speed of the electron. So maximum speed of the electron comes from the voltage. So that means we can write something like this. HF max is half mv max square, and that depends on E times V. So kinetic energy here, just the intermediate energy, right? What's happening? This potential is determining the frequency. So if we had asked to find frequency, then we would be solving for this F max here. But since it's asking to find wavelength, we need to write C over lambda for the frequency. And maximum frequency means minimum wave. Shortest wavelength gives you maximum frequency, right? Is E times V. So what is lambda minimum then? Let's do some cross multiplication. It goes up, it comes down, means lambda min can be written as HC over EV. So now you can plug in all the numbers, 6.6, 10 to the power negative, H34. This is 3 times 10 to the power 8. E is charge of an electron, and B is given here, 88,000. Okay. So that's going to be wavelength in meter. So we expect to get very small number. And as you can see, since there is negative 34, and here is just negative 19. So negative 19, when goes up, it becomes positive 19. So 1988 gonna add up. So it's gonna be 27. But there are 3 of them here, or even 4. $27 means maybe just 23 or something like that. And 34 minus 23, maybe in the order of 12 to 14, something like that. 11 to 13, I think. Most likely 12. Okay, so that's what I'm guessing. The answer negative 12. This is my guess. So close to that you should get. Okay, so that's that. Okay, hey, we are out of time, but we did not talk about Compton scattering. Again, here it's just talking about electron and photon colliding, and you can use conservation of energy, momentum, and so on. And then what you can get is, you can see after this mathematical calculation, if you cannot follow, just fine, that's fine, okay? So what you can do is, you see, so the photon is now colliding with the electron, and the scattered electron has less energy. So it's giving up some energy to make this electron move, just like in case of X-ray production, okay? So how much wavelength changes, how much energy change? So how much is the change in wavelength because of that collision is given by this equation. And this lambda c is this number here. That's called Compton shift, okay? So if you know, after collision, what angle this electron is coming out from, and then if you know that, then you can calculate how much change in wavelength is, okay? So that's what this is. So Why this experiment is significant? Because again, the photon is colliding with electron and acting like as if photon is a particle. And we are using this formula, especially the conservation of momentum formula, when we had two objects colliding and flying off, okay? So we are using that same idea. So we are treating photon as particle and getting answer. And when you experimentally test that answer, what happens? You get the same value by doing the experiment as well. So experiment supports this theory, which uses the idea that electron is acting like a photon. Sorry, the light is acting like a particle. And this wavelength here, there are a couple of things here. That's the energy of photon written in terms of momentum. And then where it's introduced, the momentum in terms of wavelength and so on. Okay, so that's the new thingy there that's coming out. So we'll start from here next time, and then we're going to move to the Bohr's theory. Okay, folks. Sorry, I took a little longer than usual time.
Thank you so much.
Oh, have a nice break, folks.